Hello everyone. This is our group video presentation for, of course, CS591 Advanced Artificial Intelligence. So it's me Sajol, and I'm gonna start our presentation today. Talking about our presentation. In this part, it was given to us to read two papers, and the first paper was titled "Learning Real-Time A-Star Path Planner for Unmanned Air Vehicle Target Sensing." And this paper presents a path planner for sensing closely spaced targets from a fixed wing unmanned air vehicle. In short term, we call it as UAV, having a specified sensor footprint. It is based on learning real-time A-star search algorithm, in which it produces a tree with feasible path, and during any time during its execution, and it produces minimum length paths, and during its completion it gives us a result that has the optimal path. To improve running time, here learning real-time A-star search algorithm is designed that terminates when there is no improvement in the path for a predefined number of iterations, and the final result is a short distance path in excessively short running times. Okay, so in this paper there are two factors that has been considered. There is dynamic limitation of the aircraft, and the next is the movement of the sensor footprint. The dynamic limitation of the aircraft are minimum turning radius and aerial sensing of the ground-based targets, which add more difficulty by requiring the footprint of a downward-looking sensor to pass over a group of targets. The path planning process uh, must also be considered, because the sensor footprint, as the aircraft follows a specified path, and the path planning approach is straightforward. In case where the targets are located very far apart with respect to the minimum turning radius of the vehicle, and on the other hand, when the targets are like closely tagged together, then the traditional path planning approach is not suitable. So talking about our problem illustration, on the left, it shows the schematic diagram of the three target sensing problem. Here the path planning uh, objective is to minimize the path length required to view all the targets, and there are three technical challenges which must be addressed, which are coupling between the path segments, utilization of sensor footprint, and determination of the viewing order of the targets. uh, and the coupling between the path segments can be seen on the right side of the figure. And if the targets are widely spaced relative to the turning capabilities of the vehicles, then the approach work well, provided that the optimal visit order can be specified. Uh, Likewise, if the targets are like closely spaced, then the coupling between the path segments due to the dynamic limitation of the vehicle can result in a poor outcome for the composite path. And the negative effect of the coupling is shown in the figure A, on the right side of the figure, which exists within the second and the third segment of the path. And on the other hand, figure B illustrates the optimal multi-target path, which clearly shows that the path segment from the initial position to the first target is longer than the myopic optimal segment, which was in figure A. So talking about the path shortening benefit of properly utilized sensor footprint, uh, like when we view the path sensor footprint, which is clearly demonstrated in figure A, uh, a sensor with a significant footprint size is beneficial. By utilizing it, we can increase the complexity of the path planning considerably. The benefit of being able to utilize a sensor footprint when viewing the closely spaced target is clearly demonstrated in the figure B. Sensor with a significant footprint size is beneficial. By utilizing it, we can increase the complexity of path planning considerably. Here, the work will only consider the constant altitude, and the constant velocity flight with a downward looking sensor. Here, a real-time A-star search algorithm has been developed that meets this technical requirement and approximate optimal. The work draws either from several different types of path planning approaches, and to determine the viewing order, traveling salesman problem, there is TSP or 3NB, also known as 3NB hard can be used. And there are some capabilities there must be addressed for effective path planning, which are the coupling between the path segment, sensor footprint, and the other is the viewing order of the targets. Okay, now talking about the discrete step path, the it is built by assembling the primitive turn and straight segments to form a flyable path. Each primitive segment in a discrete step path is of a specified length, which is ds. And when we normalize the distance, which is or the length, the ds by the minimum turning radius rt, it gives a vehicle's maximum heading change at each step, that is given by d equals to ds by rt. The number of steps in a path is given by the n, where n is equals to p n by d phi, where pn is the normalized path length and pn is equals to p by rt. The choice of which primitive to use is set by meeting specific objective for the path, such as sensing a group of targets. Okay, after assembling the left turn, right turn, and straight primitives, it creates a tree of flyable path, which is shown on the right side, and primitive turn and straight turn that forms a tree of level paths. And the objective for the path planner is to search the path tree for the branch that accomplishes the desired objective in the shortest distance. And as we closely analyze the tree, we can see that it consists of a parent node A, a set of child nodes C, a record of target sets S, where set of known targets as T. There are also some practical limitations to tree depth imposed by computer memory limits. Like for desktop computer used currently, tree depths between 30 and 50 can be implemented feasibly. And the number of nodes, as we can see in the figure, grows exponentially with the depth of the tree. Okay, so in these slides we can see there are two pictures, and on the left it shows the notation for the path planning problem, and the position and attitude of the vehicles are characterized using standard aircraft notation. Vehicle at node is given by the triplet P is equals to, which are represented by three dimensions, that is x, y, and phi, where x and y represent the inertial position and phi is the heading of the vehicle measured from the north, which we can likewise in the geometry of the nodes in the path tree, which can be represented by the equation which is on the right side, and this helps us for calculating the child configuration of PL, PS, and PR. For this work, the sensor footprint is rectangular with X sensor equals to 1.2 times RT and Y sensor is equals to 0.5 times RT, and its center is located directly beneath the vehicle. Okay, now to further continue the presentation, I would like to call Divya.
Hi guys, I'm going to explain second part of the first research paper. Now I'll start with initial heuristic. Uh, the LR the LRT A star search is a primary criteria that HI less than or equal to HI plus 1 is always true for any node I, and the explanation for this is straightforward. If a node on the ideal path overestimates the distance to the target, then the search may never reach that node and hence never identify the best path. And admissible heuristics are the heuristics that comprehensively estimate the true path length and determining the proper initial value for these heuristic criteria. In this LRT A star search, the tree search problem, heuristics are estimation of the distance required to finish the remaining jobs from the present node. Because we know the vehicle must drive at least the far to the achieve two objects, the easier technique for calculating heuristic to utilize the distance to the forest target as the initial heuristic value. And in the branch terminals, the memory management and path tree trimming are critical for LRT Estas tree search to operate well. And when we presently investigated, the branch exceeds the current optimal path and the current node terminated by removing its children and setting its heuristic value to the infinity. If all nodes if all nodes children have infinity heuristic values, then the node dead end and can be terminated similarly. The heuristic all can also be used for all cull nodes from the tree because the heuristic values of the node is always less than or equal to the actual path length. Can you move to the next slide? Um, in this slide, I am going to explain about path tree size. We should calculate the path tree size in the node between the nodes. The size of the path tree is a key issue while searching it. The size of the tree grows very quickly as the step size lowers, and making investigating the tree a time consuming operation. Whereas a search will not need explore all nodes, there will be a huge number that must be evaluated, making the search lengthy and requiring a large amount of memory space to keep the nodes visited. And the results between the two single nodes is potential field path planning to techniques are used to start the LRT A star tree search for this study. And the source for this technique is the target that the closest to the vehicle, and the potential field algorithm plots a path to the target. Once we have like accomplished the path, that first goal, you'll able to go to the next node. In this slide is about LRT start research validation. In the validation, we need to do a comparison. We need like a comparison was done between the path that obtained by the LRTA star algorithm and the path found using a brute force global search based on Dubbin's paths, highlighting the benefits of the LRTA star tree search. And to mimic the vehicle traveling through the target points, the size of the sensor footprint for LRTA algorithm was lowered. In the next slide, we can see the figure that explains. Uh, Once go back to the back slide, Sajal. I'll explain the last point. Yeah. That figure explains the tree search yields of minimum length path that nearly identical to the brute force global search with LRTA star path using only 0.5 percentage longer. Can you skip to the next slide? Thank you. In this figure, we can see the LRTA search paths for pinpoints and large sensor footprints. The figure A explains the pin plots uh, for approximately optimal. Okay. Yep. The running time for algorithm is described by the number of the nodes visited by the search to present running the data in the platform independent manner. This is not the same as the number of enlarged nodes from the path tree, but rather the total number of moves from the nodes to node during the tree search. The result of the path length and the running test to demonstrate that the step increase without affecting the path length performance significantly. These findings suggest that there are trade difference between the path length performs and speeds. More efficient path take longer to compute. My friend Ashok will continue from here. Ashok, you are in mute, Ashok.
Thank you, Divya. Thank you, guys. Thank you, Sajal. So today I am going to explain KNN LRTS search. So the title is going to be like simple subgoaling for real-time search. There are totally 6 goals, which comes under the main part like LRTS search. So when I come to the first part, it is an introduction. No, yeah. And the second part is sub-goal database construction. The third part is runtime search. Fourth one is properties. Fifth one is imperial evaluation. And the sixth one is conclusion. Next one. Yeah. When I come to introduction, the real-time heuristic search algorithms fulfill a consistent bound on how much arranging per activity and autonomous if is there any issue of size. Accordingly, they increase as well. And if I come to the property wise, the property would make them appropriate for computer games where artificial intelligence control specialists should respond rapidly to client orders and to other specialist actions. On the drawback, ongoing hunt calculations utilize learning strategies that uh, habitually lead to unfortunate arrangement quality. Furthermore, and the circumstances changed as the late with another calculation. The main search algorithm which we propose is the LRTS search, which endorse to eliminate advancing via naturally choosing sub goals. And in this paper, we propose an easier and more memory productive method uh, for uh, for our goals like sub goals. Next, yeah, here are 4 diagrams which we can describe like a basic to show the DLRTS search. Next one, yeah. The second part is sub-goal database constructions. In this, our inspiration is to hold the LRTS search great execution while improving on calculation and loosening up memory requirements. The most memory consuming piece of the LRTS search lies with its sub-goal information base. And the second one is to fabricate the data set. The LRTS search first edited compositions, the guide, and utilizing the function reflection plan of PRA search. And the third point is a lattice based map. And there are 3 points like ABC. In A, it is changed over a diagram, and in B, which is then the goal that each club of unique states turn into a solitary theoretical state. And the C part is when the deliberation is finished, a ground level state nearest to the inner circle, which is picked by the representative for the theoretical state. Next, and the third part is runtime search. In this, some of the figures shown in the PDF, like the figuring a subgoal for each pair of states is improvable for any non-trifling guide. In this way, more often than the condition, the specialist and the objectives won't be in the data set which are not available in data list. Those are called as sub objectives. Thus, the specialist cannot investigate its careful objective, however, should sum up from accessible like state objective sub goal records. So the third point is one broadly involved but straightforward instrument for runtime speculation is K, that is closest path. And we can also say that closest neighbors too. And this can be found in a novel called Cover and Heart in 1967. The thought lies with finding K closest cases to the central concern, joining their pre-computed answers involving the mix as the arrangement. Next, the fourth one is properties. When I talk about properties, there are about 5 points, like as well as being ongoing KNN LRTS search is likewise complete since it tracks down its objective in limited measure of time, assuming that the guide is limited. To be sure, each sub-goal, the specialist decides to go to the next line. It is as a ground part. And if I go to the third point, same associated part as begin, and it is in same similar part. And the fourth point, so the specialist will continuously arrive at its sub goal, and each sub goal can be utilized, all things considered, in one line. And the fifth part is the number of sub goals is limited, so in the most pessimistic scenario, the specialist will visit every one of them and prior to the running LRTS search to the worldwide objective. The fourth part is imperial evaluation. On each guide, we ran 128 unique pathfinding problem occurrences. With this, we can say around 100 to 150 problems. And the second point is every information point we present is an asset age of 1024 unique pathfinding look, like 8 guides, 128 pursuits on each. And the third point is the pathfinding calculations involved on octile distance as the heuristic. And some of the calculations based on their chip size, like 150 by 141, there are like 21,150 states, and there are some of the sizes like 163 by 160, 195 by 190. We can clearly see by the difference. These are the 8 maps used for the imperial evaluation. Next. And finally, we can conclude as a the essential drive behind this work was foster another superior execution, constant pursuit calculation appropriate for the pathfinding in computer games. Like as we told you, in artificial intelligence, by loosening up memory requirements by this technique, as we call like DLRTS search. So a present status of the continuous inquiry calculation, the new calculation KNN LRTS search offers clear advantages of pathfinding applications in computer games. Not exclusively is its information-based calculation less complex to execute than the DLRTS search, and straightforwardness of execution and light memory impression are positive credits and AI calculations in computer games. Next, that's all. We are done with our presentation. Thank you so much, guys.